All right, we are good to go, and it's a great pleasure for me to welcome on stage someone from the main sponsor of this conference. Mirco is from Vision, and Mirco Planamente is an ex-PhD student and now a PhD from the Politecnico of Turin. He was with the Italian Institute of Technology, and now is a research scientist at Vision. And he will be talking with us about Egocentric Vision, which is weird as a title, so it's up to you in the next 40 minutes to explain to us what it means. Thank you. The stage is yours.
Hi, everyone. Thank you for the introduction. I am Mirco Planamente, and today I want to talk about Egocentric Vision. Let's start to introduce the setup. Actually, it's super simple. It's just a camera that is wear by the user during the activity, normal activity, and can follow the user in order to record data in a hands-free fashion. And in this slide, we can see some frame of what kind of data it can be recorded by this particular setup. Let's move on, and we talk about popular device in this context. Probably many of you know the Google Glass. It's an old project, or the more recently device that is the collaboration between Meta and Ray-Ban. Unfortunately, for the first project is a dead project because it goes on the Google Symmetry. And for the second one, for most of you, probably is just a fancy way to make picture or in nothing more. So the question that we try to answer today is why should we want to wear a camera nowadays? And first of all, we can avoid this weird situation, in particular this one, in my opinion. So make a fancy way to make picture is useful sometimes. But the second real motivation is that can unlock a lot of application. Let me say also can change the way that a human can learn information or assist during daily activity. Can also change the social interaction or the way to design a new kind of project. Let me show you also another interesting direction that is the collaboration with robot. For example, we can learn how the human interacted with the object, and we can transfer this knowledge directly on the robots. And of course, there are a lot of other, let me say, interesting applications. As all the project in AI, we need to talk about the data. That's the most powerful part, let me say, to unlock interesting application. I want to just show you that the idea of wearable device is very old, and it's interesting for me also the fact that more than 40 years ago, there is the idea of wear some device like a computer, and the idea that this computer interact with people is in a multimodal way. Now we can just show how we can, let me say, group the research in data collection, the effort by the research to collect data in three groups. First of all, the modality. And in my opinion, it's really interesting to see how different are the way that we can collect this particular setup of modality, and also different modality in collaboration with the external camera or other sensors, so you need to synchronize. And the research made a lot of interesting, let me say, way to collect them. And the second, probably the most important part, is the annotation, because actually there are a lot of effort to annotate video data set, in particular if you want to perform some task like action recognition. For example, you need to recognize the object of the interaction, so you need to annotate the object during frame by frame, but also the action that are performed, or some like the segmentation part, the skeleton of the user, that are also another interesting direction for future tasks. Very quickly, there are a lot of applications where the research study this particular setup, and very quickly I just show you some interesting direction, for example, sports, where you study indoor or outdoor sports, or data that are recorded by using a multiple device, or segmentation task, action and object interaction analysis. And also another direction is try to use different camera and try to synchronize everything with first-person information, and in order to build an embedding, a model that is able to recognize the action from different perspectives. And of course, there are a lot of interesting and very challenging tasks in this context. The two datasets that, in my opinion, are more important and, let me say, increase a lot of the interest by the research, and not only in this topic, are these two, that is Epic Kitchen and Ego4D. For the first, is the first large-scale dataset in the context of kitchen, and the game change of that this kind of dataset introduced in the research let me say, journey, is that they propose dataset and also different challenges that are still open in order that people can participate and in order to produce some results that are really compared with the state of the art. So you have just the data, you don't have the, let me say, the label for the test, and this way you are forced to produce something that really works. And the other particular characteristic of this dataset is that it's collected in a natural way. So the idea is that to just give the camera to a user and in a kitchen, and it records a lot of video in a continuous stream, and only after the collection they annotate at a different level from the action, from the segmentation, and many other. For the second, it's really interesting because it's bigger, and it's not only for the kitchen, but they try to collect, let me say, all the kind of contexts that are feasible in the world. There are more than 3,000 hours of collection. Of course, it's not just a single project, but it's a project that made by a consortium of university, and not only. And they unlock also, in this case, different tasks and challenges spanning from episodic memory, so it means recognize where something happened, or other tasks, for example, so forecasting, so try to predict the future action of a person can do. So now we talk about, we have seen the data set that is the main part of this research, but also the second part is the architecture, so what kind of architecture we can use. Of course, a lot of architecture are hereditated by the video understanding in general solution, and this is just a picture about the literature of general video understanding. So very quickly, I just give you some insight about this paper. For example, the first solution is try to reuse the same architecture of image classification and try to bring them and adapt for video. Of course, in this way, we make a lot of it's hard to encode temporal information because we just use a 2D stream and you don't have anything that encodes the temporal information, and sometimes is useful to recognize the action. We can move on and we can see the temporal information like a third channel, let me say, a third dimension, and we can extend the convolution to also this direction. And we can introduce a 3D convolution. Of course, even if the idea is smart, in my opinion, there are some drawbacks. For example, you need a huge pre-trainer, a different pre-trainer with respect to the standard ImageNet, because you have a 3D convolution, so you need to make a pre-train on a large-scale video dataset. At the same time, you have an increase of model, and let me say the performance are not so far with respect to the other 2D or mixed architecture. So it's hard to use because you require a lot of time to train, and it's not probably the best solution to bring them in the egocentric context. The third solution is to adapt to the recurrent neural network, and in my opinion, it's still a valid solution. I suggest you this paper just because it's the simple way to adapt an existing architecture in order to work on egocentric action recognition. It's just a backbone that is extract feature, and then use an RNN to encode the temporal information. Oops. We can move on, and we can talk about TSM, that is, let me say, a good compromise between a 2D operation, but with the idea to allow the possibility to extract the temporal information. How? It's simple. They just introduce a shift among the channel dimension between frames, and this allows the network to encode this operation. It's one of the most interesting architecture, in my opinion, because you are independent from the real backbone, and you can use in the context, depending from the context. If you need to go fast, you can use a small backbone and apply this solution. If you need, let me say, just to analyze video, you can extend also to more recent architecture. So it's just a way to reuse something that already exists in more smart way. The last, of course, is the attention. I just put this paper, but the research in this direction is today, let me say, really interesting. I think that this one is one of the papers that try to say, okay, we need also optimize the attention module in order to works well or better for the video context. Let's just give you two other papers that are really interesting, not only from the point of view of architecture, but from the point of view of the pre-trained. The first one is Omnivore, that is always a VIT module that is learned, try to use multimodal information in order to encode all the modality in a same space. And it's used in the Peak Kitchen Challenge, and personally, even if it's not trained on Egocentric Vision dataset, the fact that they use other modality allow the model to learn something that is robust across domain. We can move on, and the second paper that, in my opinion, is important for the point of view of the pre-trained model is this paper, because there is one that tried to learn information from Ego4D. That is the first large-scale dataset in Egocentric Vision, and the effort is to allow to give the possibility to train with all these datasets. So this is the overview, but let me just give you the best advice I can give you when we start to work on video. And usually you have a model that tries to encode frame or clip information, and then a part of the architecture that encodes temporal information. And of course, train end-to-end is the best solution when you need to train, when you need to learn a new task. But sometimes, in particular, when you work with large-scale dataset and you don't have enough resources, make this is very hard because it requires a lot of time to encode the feature, the time information, and also you have a huge back size. And the advice that I can give you is try to split this procedure and use a good backbone in order to extract frame or clip information, maintaining this information freeze, and then use just a second part that is trained. And in the first part, you can save the feature and work only on this. And for the second part that is instead is trained, I recommend you to start from this paper that is called Temporal Reasoning. It's a simple module, but the idea behind this solution is just try to simulate what the human already done. It's just if you give two frame, you automatically can infer which action is performed inside. And the idea behind this paper is try to simulate this behavior. Actually, it's just to give you some features in input with a uniform sampling, and then you can learn how to solve the task of classification, for example. We can move on, and if you are interested in video understanding, I recommend you to start from this paper, because sometimes it's really hard to understand the literature, because the comparisons are not always fair. And in this paper, they, first of all, try to put a baseline from the architecture in video understanding, and also they show how sometimes the improvement in performance are not due to a really backbone that can extract information from the motion or temporal information, but just because it's a bigger architecture. And the second fact that they show is that the comparison is unfair just using a different sampling in the procedure. So if you need to understand which architecture is really better, or how compare architecture, this paper is really interesting and well written, in my opinion. So now we need to ask why we cannot yet have a really smart glasses that can help in our daily activity. I found a Reddit with a similar question, and the answer is quite simple but true. And so now try to give you some insight on which are the problems related to this context. First of all, when you, let me say, interact with an object and you want to recognize the action, the interaction with the object itself makes hard to recognize the object, because you have the occlusion of the hand, and in some other way you have some difficulty to recognize the object, and this is obviously a problem, of course. The second is the motion. You have a motion that you introduce to perform an action, at the same time the motion of the head, so the ego motion, and these two motions sometimes are not related and makes more complicated for the architecture point of view extract the relevant motion information that are fundamental to recognize an action or understand the video. The second one is actually a problem that still exists in computer vision stuff. It's called domain shift problem. Let me just give you an insight about how this problem burns. Suppose that you have a model trained on a specific environment and you want to recognize the object present in the environment. If the environment is the same, your model probably works well. But when you change the environment, so you change the condition that you have on your test set, probably the performance goes down. And the reason is that because there is a different distribution between the data that come from the training, or we call also the source data, and the test data. And this different distribution is called domain shift. And of course, if you think about the egocentric context, we can learn some action in a specific kitchen, in this case, or in a group of kitchen, but generalized to every kitchen in a world is really challenging. So the last is just some insight, of course, about the privacy problem related to this topic. We can move on, and this is just obviously sentence, but it's actually the problem that what we see is not always feasible for the architecture to recognize it. So in conclusion, we can say that in this context, we have more information with respect to a third-person, let me say, task, but with more problem. And today, I try to give you some insight how we can solve this problem, or at least avoid when it is possible. My idea or my solution is based on three aspects. The first one is the importance of multimodal information in the egocentric context. And the first modality, the second modality, is obviously the first is the RGB stream, is the optical flow. I tried to give you the insight about this modality because it's not a real modality, but it's estimated by the first RGB stream, and it's the motion between two consecutive frames, and you can extract the horizontal and vertical motion, and you obtain something like that. Of course, in this case, in order to reduce the drawback of the camera motion, we also removed them in order to have an information that are more related to the motion of the hand, that are the characteristic one to recognize to understand the video. We can move on, and we can just give you an insight about, okay, we have a kitchen or other context, and we have a lot of objects, and during the interaction with object, we can have characteristic sound that could be useful to recognize the action. And also the camera or the microphone is very close to the action itself, so the sound is another information that could be really useful to recognize the action. So we want to use both the three information. We have three architecture, different architecture, and we focus on how merge the information in order to solve the task. Unfortunately, this is not always the best practice, or at least it's the best practice, but learn multimodal information is not always simple. Indeed, these are really interesting paper because they show this aspect. They prove how sometimes having multimodal information does not guarantee you to have a better performance or the optimal one. And they say that the reason of this problem is due to the fact that the different modality overfit a different rate. And this way you can have a modality that can dominate the other. For our solution, we also want to achieve other two, let me say, peculiarity. That is, the first is try to generalize to every kitchen when it's possible. So exploit the multimodal information in order to perform and achieve this goal. And the second is, let me say, an interesting characteristic that is fundamental to limit the drawback of domain shift problem and give the possibility to the network to adapt a new context. In order to perform this, we want to follow the domain adaptation strategy that consists to use the source domain, that means the data that you have with the label that you learn a task, together with the target domain, so we can collect free video on a new environment without annotation. That is the main problem when you want to learn something, and use the training data with the unlabeled target data in order to reduce the domain shift. Of course, that should be done during training. So this is the goal that we want to obtain. Let me introduce a solution that we worked during my PhD that is called RNA. I just want to give you the insight about how this new loss, so it's just a loss, so the peculiarity that you can apply to every model, but not only in the context of egocentric vision. And the idea is that, okay, we have the problem that when we train a model in multimodal fashion, probably the performance that we obtain are not the best. In this case, we obtain an improvement, but when we analyze what each model learn is not the optimal one. Indeed, in this case, the RGB suffer with respect to the audio. And we introduce a solution that we want to achieve, we want to measure why and what happened at feature level during training, and we want to try to find a metric that tell me what is the problem behind this approach. We noticed that introducing a metric, in this case the norm of the feature, we can measure the quantity of information that each modality learns during training and extract from the single modality. And we noticed that the imbalance in the accuracy in this case is equivalent to the imbalance of this metric. So the RGB suffer because they learn less information with respect to the audience in this case. And we noticed that forcing during training the balancing between these two quantities is just a simple regularization. We have obtained an improvement about the multimodal solution, and of course we analyze that also the single modality perform better. So it's just a consequence of this loss. Even if the improvement is not so big in this case, we analyze the important things that is not so related only to the context of egocentric vision, but we apply in other work to different modality and different contexts, and the improvement in domain generalization and domain adaptation performance are really good. In particular, we noticed that in the last two we have a huge improvement because in this case we work on a setting. It's just an image classification task where the training data is data that are simulated, synthetic data in that case. It means that the domain shifts are huge. More the domain shifts are huge, and the better are the domain adaptation of approach. So I apply also this solution to the challenge, and we achieved the third position for 2 consecutive years. So let me give you the last part of the multimodal analysis related to the egocentric vision, and we need to make a step back. We know that the RGB information is feasible because we can use a wearable device to collect them, but unfortunately the performance, in particular in cross-domain, are very poor. Instead, the optical flow information is not a real modality because we need to complete them and then use it in a backbone, but at the same time it's really robust to the domain shift, of course, because you don't suffer between the change of the appearance. It's, let me say, invariant to the appearance. So we want to find a new modality that have the same benefit of the optical flow, so focus more on the motion information instead to the appearance information in order to achieve something that is more robust to cross-domain. And of course, that is a real modality. Let me introduce a new device that is called DVS sensor or event camera that works differently with respect to the standard RGB camera. Like in this example, we see that it focuses only on what moves inside the video, and when nothing moves, the output is equal to 0. To better understand the differences, actually they try to focus on the light variation in the image and detect in positive or negative this variation is detected or not an event. So an event is just a list of tuples where we have the x and y position, the timestamp when it's detected, and the polarity, of course. This modality is relevant for us because it's robust to background. Also, it does not contain motion blur because it's go really fast with respect to the standard RGB camera, and it's invariant to the illumination. So it's perfect for our context But we have the problem that it's hard to compare this new modality in egocentric vision because we don't have this new modality. And at the same time, collect a new dataset is super expensive, and also I didn't have an event camera in my lab. So we need to find another solution, and also in this case, we investigate how we can simulate this information. Let me just give you the insight about our pipeline. We introduce an Epic Kitchens, that is the version of the Epic Kitchen with this new modality, even if it's simulated. And the pipeline to simulate is quite simple. We just take a video, we increase the frame rate of this video using an architecture called super slow-mo, and then using a sim simulator that allows us to extract this event data from the video itself. Then we propose a way to adapt easily the existing architecture think for RGB data, and then propose also a strategy to exploit the optical flow information only during training in order to better extract the relevant part for the event information, considering also that we don't have a pre-trained on event data. Very quickly, you can see the results. We achieve the better performance with respect to RGB, and also with the other two solutions that we introduce, the improvement is evident. It's not achieved the performance of optical flow, probably also because we don't have an architecture thinked for this device or thinked for this modality that is quite different, but it's really interesting, and it's allow also promise resulting to invest better for a device that can extract this modality by yourself. The last part of this talk is related to the privacy. Let me just give you some insight. Of course, respect to third-person video, anonymize the video of third person is quite simple because you can just blur the information of the face and you can still able to recognize the action. Unfortunately, in the egocentric vision, we have a false sense of privacy because you don't have the face of the user in this case. And let me just introduce this paper that they, first of all, prove that it is possible to recognize the user by the intrinsic motion of the camera, so by the walk or by the gesture of the user. So it's really hard because, respect to the standard third person, we cannot separate this information. I mean, you cannot blur some part of the information of the video because it's essential to recognize the action. And they propose a solution to solve this problem. And the idea is try to, okay, I want to let me say, transform the information present in the video, but without reducing the performance of a standard approach like action recognition or whatever. And the idea is just to perturb a bit, learn how to perturb the image, and with an adversarial approach. And after that, we can obtain, in the last row, we see the approach. And the idea is just to obtain a video that is really, really small, with a small variation in the 3D, let me say, perception of the image, but allow to the model to maintain the same performance. So let me just give you some advice that probably are not relevant for only for the egocentric vision, but we can extract from this talk. First of all, in my opinion, the two backbone that I show you, a Omnivore and EgoLLP, could be also useful in other contexts, and probably could be an alternative to the state-of-the-art Dino V2 or Clip for extract feature. The second and the third, of course, are the relevant part of how multimodal information could be useful to perform domain adaptation and domain generalization approach. And the last is the importance of event. Let me just give you the last insight that event data can be also used in image context, for example, image classification, and we can extract or simulate them also in this case. It means that if you have a model that works only with RGB, you can easily simulate this other alternative modality and works with two-stream and can probably already improve your backbone just using this approach. I think that it's quite finished the talk. 1 second, let me just show you the last two slides. Probably I hope to convince you on the future of egocentric vision. This is my idea of egocentric vision. And if you're interested in some papers that are published or that are, let me say, included in this talk, I give you this rep online with all the papers that are published in this context. Thank you for the attention.
Thank you very much, Mirco. It was not easy to give this talk in this setup, and you nailed it. Thank you again. Questions? Now we have time just for one. You were very quick, so.
Hi, Mirco. First of all, thank you for the comprehensive presentation. You explained very well. So I have just a quick question. Could you explain a bit more in detail how did you generate the event data without having an event camera?
Yep.
Like from the RGB frames, right?
On the NAP kitchen version. Okay, yeah. Event camera, respect to the standard RGB camera, works with a high frame rate. So the first step is to increase the standard frame rate of camera. And to perform this task exists a lot of architecture. In this case, we use super slow-mo, but I think that nowadays exists an improvement version of this architecture. And when you have this simulated version, exists a simulator that gives you this pipeline, let me say, this increased version of grayscale images. You can just give in the input and just give you this cloud of information. Unfortunately, the event is just a list of tuples, not an image. So you need to also transform this information in something that could be learn and teach using the standard RGB, let me say, 2D convolution architecture. So the idea is to bring them all this cloud in order to obtain, let me say, a voxel grid representation. And when we have this representation, instead we pass from this cloud of points to this representation that we see in the bottom part of the slide, that is like an edge detector, but with the difference that you have the direction of the motion, because you have the positive and the negative motion.
Okay, thank you so much.
You're welcome.
Again, a huge round of applause for Mirco. Thank you very much.